Hello, my name is Isaac Wenger, and this is Lab 3 Black Hole. The purpose of this lab is to demonstrate Newton's second law and how it relates to momentum. For part 1, you find the mass of the black hole using the momentum of an orbiting star. I found the mass to be 2.05 times 10 to the 34th kilograms. For part 2, you find the initial velocity of a spacecraft so it can escape the planet as well as fly around the black hole without crashing. I found the initial velocity to be negative 4.8 times 10 to the 7th in the x direction and 2.51 times 10 to the 6th meters per second in the y direction. The physics involved is Newton's second law, which states that force is the change in momentum over the change in time. This can be rewritten into the velocity update and position update formulas. Another key concept is the gravitational force equation, which states the gravitational force exerted on one object from another. And another key concept is the perpendicular and parallel force. Perpendicular force is equal to mass times velocity squared over r, where r is the radius, and n hat is points towards the center of the circle. F net parallel is a change in momentum over the change in time, where p hat points in the direction of the momentum. For part 1, you find the mass of the black hole. This is the initial conditions as well as the coding. First, you find the initial momentum and final momentum. Then you find F net. And then you find F net in the parallel and perpendicular direction. Finally, you take the gravitational force equation and you solve for the mass of the black hole, and then you plug everything in. I found the mass to be 2.05 times 10 to the 34th kilograms. The net force would be 1.03 times 10 to the 29th, and all the rest. To find the net force on the star by the black hole, you would use the gravitational force equation, and you would just plug in everything you know. You know the mass of the black hole, you know the mass of the star. You have to take the position of the star minus the position of the black hole and plug it in. So net force is all the forces acting on an object in the system. Its parallel and perpendicular components measure the forces of a specific action. The rate of change of momentum measures its mass times velocity over time, and those are the same thing when the mass is constant. So for this scenario, they are basically the same thing. Some possible sources of error is the code I wrote may have not been all that correct, and the model may have rounded different components, which would explain why the mass of the black hole was constantly different. For part 2, it is don't crash. Here is the initial conditions with the mass of the black hole, and through trial and error, I found the velocity of the ship, initial velocity of the ship. So for the code, you are finding the gravitational force of the black hole on the planet, and then you are finding the gravitational force on the ship on the planet, and you are finding the net force from the ship and from the black hole, adding them together. Then you find the gravitational force on the black hole on the ship, and the gravitational force from the planet on the ship, and then adding those together to get net force on the ship. From there, you find the planet velocity and planet position, as well as ship velocity and ship position. The result is that the planet orbital speed is 1.17 times 10 to the 7th meters per second, and the spacecraft escaped without crashing. Yay! So I could not get the spacecraft to enter a stable orbit with the black hole. For some reason, it kept either crashing on takeoff or crashing into the black hole. So, yeah. Some possible errors would be the model maybe rounding the gravitational constant g, which means that the spacecraft receives slightly different forces on it through each simulator run.